Good afternoon. Welcome to EduSet Network. Friend, you are watching EduSet lecture, and as you know, we have organized a series of lecture on use of statistics in research method, and we have covered a number of statistical tools. And today we are going to discuss the tools correlation and regression. And for discussion on this very topic, we have in the studio Dr. S.K. Pandey. He is presently teaching at Ford School of Management in New Delhi, and he has expertise in the research method. So I hope his knowledge and experience will help us to understand this statistical tool in a new way and in interesting way. So on your behalf, I welcome Dr. Pandey. Welcome you, sir.
Thank you. So good afternoon, friends. This is the fourth session in the lecture series on use of statistics in research methods. Today, after yesterday's analysis of variance tool, we will be talking about correlation and regression. Correlation and regression is used very extensively in almost all branches of management, marketing, finance, HR, etc. And today we will be covering these things in our lecture. First, we will talk about the correlation, which is called as product moment correlation, or also called Karl Pearson correlation of coefficient. Then we will talk about partial correlation. Also, we will talk about a little bit on non-metric correlation. Then we will talk about regression analysis, which is done after correlation has been found significant. Then we will take bivariate regression, which has got only two variables. Then we will talk about statistics associated with bivariate regression. Then we will talk about how to conduct a bivariate regression analysis. And in this case, we will take an example and will try to use Microsoft Excel in conducting the bivariate regression analysis. Then we will estimate the parameters of bivariate regression. We will also find out the standardized regression coefficient as well as unstandardized regression coefficient. We will do a significance testing of whether the hypothesis of not having any relationship can withstand or not. Then we will also test the strength and significance of association between the variables. We will also predict the prediction accuracy of our model, and we will also look at the assumptions that we have while doing regression. Then we will also take in the same very example, we will add another independent variable and use this as an example for multiple regression. Then we will also talk about a little bit of statistics of multiple regression, and we'll conduct the multiple regression using Microsoft Excel as we did it for bivariate regression. Then we will talk about certain issues which we may encounter while doing regression, like multicollinearity, and how to deal with this type of multicollinearity and other issues. Then we will also talk about relative importance of predictors. In the end, we will summarize what we discussed, what we tried to understand in today's lecture. So the product moment correlation, which is denoted by small r, summarizes the strength of association between two metric, interval or ratio scale variables, say x and y. A very important thing which we can note from our yesterday's lecture was that when we were discussing the relationship between analysis of variance, correlation and regression, there we discussed, and analysis of covariance, there we had discussed that when both the variables, independent and dependent, are on a metric scale, either ratio or interval, we should do what is called as correlation or regression. However, today we will extend our logic and say that even when both the variables are on ordinal scale, we can do what is called as non-metric correlation. This R signifies the straight line relationship between x and y. A very important thing to note in this is that we are finding a linear relationship. So if we say that if the R value comes out to be 0 and it ranges between 0 and 1, we can at best say that there does not exist a linear relationship. We cannot say that there is no relationship, because although there may not be a linear relationship, but there always may exist a non-linear relationship, which may be in the form of a quadratic, a curve, or something else, exponential, logarithmic, or many other type of relationship. So R is equal to 0 only signifies that there is no relationship which is linear in nature between the two or more than two variables in question. As it was originally proposed by Karl Pearson, this is often also called as Karl-Pearson correlation coefficient, and at times it is also referred as simple correlation, bivariate correlation, or merely as correlation coefficient. So if nothing is mentioned, then correlation coefficient usually means Karl-Pearson correlation coefficient. For a sample of n observations between x and y, usually y is considered the dependent variable and x is considered the independent variable or variables. The product moment correlation or Karl-Pearson correlation coefficient can be calculated as sigma ranging from 1 to n bracket xi minus x bar multiplied by yi minus y bar upon under the root xi minus x bar whole square summation, then square multiplied by summation of yi minus y bar whole square. If we closely look at this formula, we can know that if we divide it both the numerator and denominator by n minus 1, we get what is called as covariance between x and y, and divided by the standard deviation of x multiplied by the standard deviation of y. So R is basically the ratio between covariance between the two variables with the standard deviations of x and y. As I mentioned earlier, the value of R varies between -1 to +1. It is incorrect to say that it varies between 0 to 1, because correlation or relationship between two variables can be positive as well as negative. -1 is perfect negative correlation and +1 is perfect positive correlation. All the values range between -1 to +1. Any relationship which is positive indicates that when one variable increases, the other variable also increases. We can have relationships like the expenditure on sales promotion to the increase in sales. There usually may be a positive relationship. There can also be other instances where, say, height and weight. So when height increases, usually the weight also increases and vice versa. However, there may be certain examples of negative correlation. Especially we must have some idea about microeconomics, where we talk about demand and supply and price related to the demand. So usually we find that when the price increases, the demand of many of the commodities decreases. So there exists a negative relationship between demand and price of a given product, and so on and so forth. So there are many relationships which are negative in nature, and there are many relationships which may be positive in nature. So product moment correlation ranges between -1 to +1. The correlation coefficient between two variables will be the same regardless of their underlying unit of measurement. As we have seen that correlation coefficient is actually a ratio, so the unit of measurement does not affect, because it gets cancelled out. So no matter we measure the units in any unit of measurement, the relationship or the value of R will remain the same between the two variables. It is also immaterial as to which variable is considered as the independent variable and which variable is considered the dependent variable. The correlation will remain the same whether we consider any one of them to be x or y. This is the example that we are going to take for today's discussion. As I have already explained that we will be talking about this example as a bivariate regression example as well. as well as correlation, as well as for the multiple regression example as well. Here if you see, we have calculated responses from 12 respondents numbered 1 to 12, and we have asked, or we have measured 3 variables. The first one is the attitude towards the city. So all the respondents are living in some city, and we are asking their positive or negative attitude towards the study, towards the city, and this attitude is measured on a I think 0 to 12 point scale, and 0 being very little positive attitude, and or rather a very negative attitude, and 12 means a very high positive attitude towards the city. Then we think that this attitude may be dependent on the duration of residence in the city. So people living longer in the city may be different from the people who are living for a smaller duration in the city. Their attitudes may be different. So we believe that perhaps duration of residence has got something to do with the attitude towards the city, and duration of residence has been measured on a ratio scale. We have asked the direct question as to how many years have you been residing in the city, and people have given responses to that. Then the third again is an independent variable, importance attached to weather. It may be that people may give different importance to the weather in the city, and this importance given to weather might affect the attitude towards the city. So importance and duration of residence, these two become independent variables, and attitude towards the city is the dependent variable. So first, when we will do regression, we will take only one of the variables, duration of residence, and do a bivariate regression, because there will be only one independent and one dependent variable. Later on, to explain multiple regression, we will be taking duration of residence and importance attached to weather both in the model, and attitude towards the city still remains the dependent variable. So this is the example that we are going to explain: correlation, regression, bivariate, as well as multiple regression. So product moment correlation, we are from the data given previously, we are going to find out the correlation between the attitude towards the city and the duration of residence. The attitude is y and duration of residence is x, because the independent variable is usually denoted by x. So as we knew in the formula, we had to calculate x bar and y bar, because we have to find the deviation of y minus y bar and x minus x bar. So we are finding out the mean of x bar and y bar. The mean of x bar comes out to be 9.33, and the mean of y's comes out to be 6.583. Then as we have to find out the covariance in the numerator, we are multiplying xi minus x bar with the corresponding yi minus y bar, and adding all of them. This comes out to be equal to 179.6668. Then we also have to find out the standard deviation of x and y, because this will go in the denominator as per the formula, and standard deviation is being calculated xi minus x bars. So all the measurement of x's, we are subtracting the mean and squaring it, and again adding up. So we xi minus x bar whole square sigma comes out to be 304.6668, and similarly yi minus y bar square comes out to be 120.9168. Then we will have to multiply it and take a square root in the denominator, and the numerator will be 179.6668 as we have found out earlier. So this value comes out to be 0.9361. So interpreting this value of R, we can say that the Karl Pearson coefficient of correlation between the attitude towards the city and the duration of residence in the city comes out to be 0.9361. This is a very high value, because the value lies between 0 and 1, and it is also positive. So looking at the value, we may conclude that there is a very high positive correlation between the two variables, that is attitude towards the city and duration of residence to the city. interpreting it further, we can say that the longer is the duration of residence in the city, that person gives a better evaluation or has a better perception about the city. So people who have lived longer in the city like the city more, or they have a very favorable attitude towards the city. So attitude towards the city is dependent on the residence and also very positively dependent on the resident, number of years of residence. However, the same thing can be calculated very easily with softwares like SPSS, Excel, Minitab, etc. And now I am going to calculate the same value through Excel. It is the same data that we have shown in the presentation. So I have taken these two variables, duration and attitude towards the city, because we want to calculate the relationship or correlation coefficient between these two variables, duration of stay and attitude towards the city. So these are the two variables. Now we can calculate the correlation coefficient. We have to first go to data, then from data to data analysis. This type of a dialog box will appear. If you can recall, then this was the same dialog box that appeared when we were doing ANOVA, and ANOVA is still featuring as the first option. So now we have to calculate correlation, and we'll have to select correlation and click OK. This is the dialog box that will appear. It will ask for the input, and we have to select this and then go to the input range, select the entire data set from the first to the last. Then it will ask whether the data has been grouped by column or rows. The default is column, and as we see, actually the data is in column. The first column representing duration of stay and the second column representing attitude towards the city. So we have to we don't have to tinker anything here. However, if the data would have been entered row wise, then this would have to be selected as rows. Then we can go and say OK. Now if you see, the correlation of any variable with itself will be always 100%. However, the correlation with column 2 with column 1 comes out to be 0.936, and it is the same whether we consider the correlation between 1 and 2 or 2 and 1. Then the value comes out to be the same. So if we see, we are able to see that the correlation between the same variable is always 1, and the correlation between the first and the second variable, that is duration of stay and the attitude towards the city, comes out to be 0.936. This is the same value that we have calculated by using the formula and calculating the various things using the formula. So softwares like Excel and Minitab make our job very easy, and we even at times we do not have to remember the formula, and we can simply go and use these two columns or any number of columns and find out the correlation between the variables. And the interpretation remains the same, that there is very high positive correlation between these two variables. The longer the stay, the more favorable the attitude towards the city. Now there is some statistics associated with the correlation. If we square the correlation coefficient, that is, if we find the value of R square, that is equal to explained variation or the percentage of explained variation to total variation. In simple terms, this tells how much of the variation in the dependent variable is explained by the independent variable or independent variables taken together. So R square is a very important statistic because it indicates how much is the explained variation vis-a-vis how much we are unable to explain. R is usually for the sample. If we are calculating the correlation coefficient for the population, it is denoted by rho, which is a Greek word rho, and this coefficient R is an estimator of rho, which means if we want to know the correlation coefficient of the population but have calculated a sample, the sample correlation will be an indicator or estimator of the population correlation coefficient rho. And we also can test the hypothesis. The hypothesis is that correlation is not, or the correlation coefficient is 0. This is the hypothesis which can be tested by using a t distribution. The formula is t is equal to r under the root n minus 2 upon 1 minus r square. This follows a t distribution with n minus 2 degrees of freedom, and the t value in the previous case comes out to be 8.414, and when we look at the critical value in the table, we find that for alpha is equal to 0.05, the critical value is 2.228. So the calculated value 8.414 is much higher than the table value or the critical value of 2.228. So the null hypothesis that there is no correlation between the two variables is rejected, and we will have to conclude that there is very high positive correlation between the two variables, and it's a significant correlation. As I already explained earlier, having an R value is equal to 0 does not mean that there is no relationship. It only means that there does not exist a linear relationship and the two variables are not related in the form of a line. However, there can always be a curve or an exponential relationship or a logarithmic relationship, quadratic relationship, and so on and so forth between the variables. So R is equal to 0 only indicates that there isn't a linear relationship between the two variables. Partial correlation coefficient. Often in the real life scenario, the dependent variable y does not depend on only a single variable. It, like in the previous example that we took, there also can be the importance attached to weather can also affect the relationship or may also affect the attitude towards that city. So when more than one variables are affecting the dependent variable, often we are interested in knowing the effect of only one independent variable and controlling for the effect of other variables. So in that case, we calculate what is called as partial correlation coefficient. It denotes, for example, in this particular example, this is the first order partial correlation coefficient. It denotes the relationship between x and y when z is kept constant. It is denoted by r x y dot z, which means x, we are finding out the relationship between x and y, controlling for the relationship of y z. Similarly, if there are more than two independent variables, we can have second order, third order, and later order partial correlation coefficients. Non-metric correlation. When we started our discussion, we said that the two variables must be metric. That means they should either be ratio or they should be interval scale variables. However, as we move further, we also indicated that at times there can be a non-metric correlation also. If you go to softwares like SPSS and want to go for correlation, they will ask you three types of correlation. One is called as the Karl Pearson, which we have recently discussed. Then there will be other two options. One will be called as Spearman's rho, and the third one will be called as the Kendall's tau. Now, Spearman rho and Kendall tau are non-metric correlation in the sense that this correlation is calculated, or this correlation is also called as rank correlation at times. By the name rank correlation, this indicates that the data that we collect is in the form of ranks and is called as ordinal data. For example, suppose there is a dance tournament going on, and suppose there are 3 judges in the dance tournament, and the judges, instead of giving marks, are giving ranks to the various teams. Now, if we want to know whether the first judge and the second judge have given similar rankings, then we can find out what is called as rank correlation. And here we will be having in the first column the rank given by the first judge, and in the second column it will be the corresponding rank given by the second judge to the same person. So if the first participant got the rank of, say, third by the first judge, then the second column corresponding to this will have the ranking of the second judge of the same participant. So in this way we can have the various ranks, and we can calculate the rank correlation, which is also called as Spearman's rho. However, Spearman rho gives a better answer, or should be calculated when there are no ties or very few ties. Ties in rank means when the judge gives the same rank to more than one teams. It may be possible that the judge is not able to differentiate between the performance of 2 teams and gives the same rank to both the teams. In such a scenario, if there are many such ties, it is better to use Kendall correlation, Kendall's tau, rather than using Spearman. Now we come to regression analysis. Once the correlation has been found to be significant, then we go and conduct what is called as regression analysis. Regression analysis examines associative relationships between a metric dependent variable and one or more independent variables in the following ways. First, determine whether the independent variables explain a significant variation in the dependent variable, whether a relationship exists. So before we go further, we have to first find out whether there is a relationship that exists between the various independent and the dependent variable, which can also be found out using correlation. That is why correlation and regression often go hand in hand. First we calculate correlation, and once the correlation comes out to be significant, the next stage is to do regression. So in a way, regression also is finding out whether the relationship exists. We will have a hypothesis here that there is no relationship between the independent and the dependent variables, or the independent variables are unable to explain anything or any variation of the dependent variable. Once the hypothesis gets rejected, then we will move further. Then we also have to determine how much of the variation in the dependent variable can be explained by the independent variables, strength of the relationship. So there can be a weak relationship and there can be a strong relationship. So how much can we predict the dependent variable if we know the independent variable is how much of the variation is explained by the independent variables. So we are also inclined to know how much is the explanation of the dependent variable taking the independent variables together. Then we also want to structure the relationship, that is we want to find out the mathematical equation governing this relationship. Then we also want to predict the values of the dependent variable. If we have independent variables, then we also want to predict the value of the dependent variable by using the equation which we found in the previous step. Then control for other independent variables. We at times also want to know the effect of effect on the dependent variable by changing only one of the independent variables and controlling for other variables. So this also is one of the objectives, and regression analysis is basically concerned with the nature and degree of association between variables and does not imply or assume any causality. Now, bivariate regression model. Bivariate, as the name suggests, means a regression between two variables. One will be called as independent variable and the other will be the dependent variable. Like we recently discussed, the attitude towards the city and the duration of residence in the city. The equation is given by dependent variable y is equal to beta naught plus beta 1 xi plus error term. Y is the dependent variable and x is the independent variable. Beta naught is the constant and e is the error term associated with the calculation, ith observation. Then coefficient of determination, we have already discussed that r square signifies how much of the variation or what percentage of variation is explained by the independent variables. This lies between 0 and 1. Estimated or predicted value. The third objective was also to calculate or predict the value of y. If we know the values of x, then by using the equation, we can always calculate the value of y. So regression coefficients are the estimated parameters of B and is usually denoted by non-standardized regression coefficient. Scattergram is the diagram or scattergram is a plot of the values of A and B, corresponding values of A and B for all the observations. The standard error of estimate is the statistic SEE is the standard deviation of the actual y and the predicted values of y. This is actually the error. So we will predict from the model a particular value of y which we call as y cap, and there is actually a value of y for that corresponding x. So these two may not be exactly similar, and the difference between these two is the error. If you take the standard deviation of all these errors, then this becomes the standard error. Standardized regression coefficient. When we do a regression, we get two types of regression coefficients. One are called as unstandardized regression coefficients and the other one are called as standardized regression coefficients. The standardized regression coefficients are obtained by first standardizing the independent and the dependent variable by making their mean equal to 0 and standard deviation equal to 1, and then finding the regression between the two. Sum of squared errors. The distance of all the points from the regression line are squared and added together to arrive at the sum of squared errors, which is measured as a total error. T statistics, as we have found out earlier for correlation, similarly a T statistics is there for finding out the relationship between the two or more than two variables in the regression equation. So the regression equation in a bivariate case is y is equal to beta naught plus beta 1 x plus error term. Our hypothesis is that there is no relationship, which means both beta naught and beta 1 is equal to, or all betas are equal to 0. This hypothesis can be tested by using a T statistic, and only when the hypothesis gets rejected, we believe that there is a relationship between the independent and dependent variable, and regression is worth doing in this case. Conducting the bivariate regression analysis, there are various steps that we have to follow in doing a bivariate regression analysis. The first step is plotting the scatter diagram. When we have got the variables, we must plot them on a scatter diagram. Plotting on the scatter diagram will give us an idea whether there exists a relationship between the two variables, and can we fit a line, regression line in the two variables, whether there is a linear relationship that exists. Second is formulating the general model. Third is estimating the parameters, the coefficients and the constants. Then we can also estimate the standardized regression coefficient. Then we have to test for the significance or the hypothesis that there is no relationship. Then we have to determine the strength and significance of the association. Then we have to check the prediction accuracy, examine the residuals and cross-validate the model if possible. This is the equation which we have already talked about, and we are going to estimate the parameters B0 and beta 1 by using the regression equation. Now here, this is the scatter diagram as the first step between finding out the relationship between attitude and duration of residence. If you look at the scatter diagram, it indicates that as the duration of residence, which is on the x-axis, increases, the attitude towards the city also becomes more and more positive. It seems that there can be a linear relationship and we can fit in a line using these points. How to make a scatter diagram in Excel. We will now use Excel for making the scatter diagram. As you see, there are these two variables, duration of stay and attitude towards the city. We will select these two variables and then go to insert, and on the right hand side there appears scatter. So we will click scatter and select the first scatter diagram. So if you see, this is the same, exactly the same scatter diagram that we have plotted in the PowerPoint presentation. So this indicates that there seems to be a relationship of a line of a linear type between these two variables, and therefore regression should be performed. If we want, we can also fit in a line which is called as the regression line by right clicking on any of these points and selecting the option add trend line. If you see, then there can be various types of lines that can be fit in, or not even lines, various types of even curves can be fit in, like logarithmic, polynomial, power, etc. But we are looking at the linear relationship, and therefore default is linear. And we can also, in the same equation, we can find out the equation also, and also the R square, which is the coefficient of determination or the percentage of explanation of variance by the independent variable of the dependent variable. Now if you see, once we do this, a line is fitted using these points, and also we get the R square value of 0.8762, which means almost 87% of the variation of the dependent variable is or can be predicted by knowing the attitude towards the city. So attitude towards the city can be predicted almost 87% by knowing the duration of stay of the person in that city, and the equation comes out to be 0.5897x plus 1.0793. So looking at this, we know that we can first fit a scattered gram or scatter diagram, and once we have fitted in the scatter diagram, if there seems a positive relationship, a linear relationship, either positive or negative, then we can go on and perform the regression equation, regression analysis. Now what is the logic? We fitted one single line, but there can be many lines through those points. So which line can be considered as the best line? The logic for fitting that best fit line is that the error, or error in this case, is that the distance between the line and the point is the error. If all the points lie on the same line, then there is no error at all. But since not all the points, or at times not even one point, will lie on the line, we can actually find out a line which will reduce these errors, which is the line which has the minimum number of errors. So we are trying to reduce the distances between this point and the line. Now the distance can be calculated on the y-axis or on the x-axis, but since in this case y is the dependent variable, we calculate the y distances and try to minimize and fit a line which minimizes the overall errors. So the best fit line is the line which has got the minimum errors. This also gives us an idea that there cannot be a regression line where all the points are on one side of the line. This cannot be possible, because then if the line moves in that direction, it will reduce the errors. So there has to be at least one point which is on the other side. However, every point does not move the line. If we add one point, it does not move the line in a uniform way. A point which is very far from the line will move the line more further in that direction if we add, rather than a point which is very close to that line. However, no matter if we add another point, it will move a little bit that line in towards that point. Standardization, as we said, that we also at times find the standardized coefficients. Standardization is the process of making the mean of the series 0 and standard deviation equal to 1. Then we also can calculate the test for significance. As we did in correlation, we can have a test of significance or testing of the hypothesis whether there is any correlation between the two variables. The hypothesis is that there is no correlation, and it can be tested by using a t statistic. Now this is the same equation or a similar equation that we got. Attitude y is equal to 1.0793 plus 0.5897 into duration of residence, which we got by using Excel. And the standard error also is something, and it is significant. This is the output that is achieved when we use SPSS for doing the bivariate regression. R is the correlation coefficient, which comes out to be 0.936, which we have already calculated earlier. R square is the square of this R, which indicates that almost 87% of the variation in Y is explained by the independent variable. Adjusted R square is adjusted for the number of variables in the equation, and as the number of variables increase, as the number of independent variable increase, there is decreasing returns to scale. That means the newer and newer variables add very little in the explanation. So adjusted R square is the adjustment of R square, keeping in mind the number of variables. Then analysis of variance is conducted to test the hypothesis whether all the betas are equal to 0 or there is no correlation. The hypothesis in this case gets rejected because the F value comes out to be, significance comes out to be 0.000. So it is rejected, and we conclude that there is correlation and regression model is quite good. Then the equation comes out to be constant is 1.07 plus the coefficient of duration is 0.589 into coefficient of duration. This is the same equation which we see in the variables in the equation. Then standard errors are given. Beta is also given. Beta is when there is no constant, and standardization of both duration and the y is done, and the relationship is like y is equal to bx with no constant. That value comes out to be 0.936. Then we have found the t statistics for both constant and duration, and we find that duration is significant but constant is not significant. So duration, by knowing the duration, we can predict the attitude towards the city, and they are both significantly related. The assumptions in regression is that the error term is normally distributed. For each fixed value of x, the distribution of y is normal. The means of all these normal distribution of y given x lie on a straight line with slope b. The mean of the error term is 0. The variance of the error term is constant. This variance does not depend on the values assumed, and they are uncorrelated. In other words, the observations have been drawn independently. Now, on the similar lines, we can have multiple regression where the independent variables are more than one, and everything runs parallel to what we discussed. So here also the model is significant. R values have been given, and equation in this case comes out to be 0.337 plus 0.48108 into duration of residence plus 0.2886 into importance given to the weather. The beta or the standardized coefficients comes out to be 0.313 into importance plus 0.763 into duration. Significance has been calculated, and we find that both the importance and duration both are significantly correlated, and both help in explanation of the attitude towards the city. However, constant in this case also is not significant. One of the problems that we may encounter while doing regression is that the independent variables may not be actually independent, and they may also be correlated. This is called as multicollinearity and is a serious issue which we need to handle before we go on to conduct the multiple regression. So, or even regression. This multicollinearity can result in several problems, which includes the partial regression coefficient may not be estimated precisely, the standard errors are likely to be very high, the magnitude as well as the signs of the partial regression coefficient may change from sample to sample. Because of this multicollinearity or correlation between the variables themselves, the sign of partial coefficient may keep on changing. It becomes difficult to assess the relative importance of the independent variable, and predictors variable may be incorrectly included or removed in stepwise regression. So how to deal with this multicollinearity issue? A simple procedure for adjusting for multicollinearity consists of using only one variable in a highly correlated set of variables. So suppose there are three variables which are highly correlated with each other, and our independent variable, we can use only one of them as in the equation, or else we can use things like ridge regression or factor analysis, and then use them as independents in the regression equation. Alternatively, the set of independent variables can be transformed into new set of predictors, like using principal component analysis or factor in factor analysis. Relative importance of predictors. When we want to know the relative importance of predictors, we have to look at either the partial correlation coefficients, or else we can also look at the standardized correlation coefficients. These are the programs and steps which we use when we are using SPSS in Windows. Now we will go to the same example and do what is called as regression. First we will do bivariate regression. First we will do bivariate regression using attitude towards the city and duration of stay. So now we will go to data, then data analysis, then instead of correlation we will choose regression and will do OK. You will see that it will ask for y as well as x. Y is the dependent variable and x is the independent variable. So we will select for y, we will select attitude towards the city, and for x, in this case we will select only duration of stay. And then we will say OK. You see we get a similar output that we got in that we have shown in the PPT. So this is the F statistic. We see that the model is significant. The F value comes out to be 0.000 something. So the model is considered significant. R is 0.94, which is exactly equal to what we concluded earlier, 0.936 to be precise. R square value is also the same. So this is how we conduct the multiple regression. The equation is that X variable, which is the duration of stay, is multiplied, the coefficient comes out to be 0.589, and intercept or the constant is 1.079. So the equation becomes y, which is the attitude towards the city, is equal to constant, that is 1.079 plus 0.589 into duration of stay in that city. And rest of the things I have already explained. When we are doing multiple regression, we will use the same data and again do a multiple regression. In this case again we go to data, data analysis, regression, and we have already selected the y. For x we will select both the duration of stay as well as importance given to the weather, and we will go and say OK. So this is the output of multiple regression, which is exactly similar to what we found and we have shown in the PPT. Now the equation becomes 0.288 into second variable, that is the attitude, that is the importance attached to the weather, plus 0.48 into the first variable, that is the duration of a stay, plus constant as 0.337. So in this way, if we know what is the value of x1 and x2 and constant, we can always calculate what will be the attitude of this person towards the city. In the end, if we wanted to know which of these two variable is more important, we can go and again do the same data analysis, regression, and instead of regression coefficient, we have to take constant as 0, so that we get the standardized equation. We can go to again to sheet 1 and we can go to data analysis, regression. The dependent variable remains attitude towards the city. The independent variables are the two, duration of stay and importance given to the weather. And this time, instead of having this thing, we have to have constant is equal to 0. And this is the equation that we get. Now, if we look at the constants and the coefficient, we know that x1 variable is 0.497 and x2 is 0.308. So, first variable is more important in explaining the attitude towards the city. That means the duration of residence explains more than the importance given to the weather. So, looking at the standardized coefficients, we can know which variable is more important in explaining the dependent variable. So, this is all about regression, and we can use this for many applications in both marketing, HR, finance, and other areas. This is how we conduct regression analysis, partial regression, as well as multiple regression analysis. Thank you.
Well, this was the numerical side of things, how do we calculate, and what the meaning one can derive from this calculation.
The meaning that one can derive from these calculation is first looking at the R value. The R value tells two things. First, it can range between -1 to +1. So higher the value, the more is the relationship between the two variables. So suppose the R value comes out to be 0.9, like in this case, it means that these two variables are very highly correlated and the relationship is very, very strong, which automatically means if we know one variable, we can very accurately predict the other variable. The second thing is the plus and the minus sign. Plus indicates that there is a positive relationship. When one increases, the other one also increases. Minus indicates that there is a negative relationship. When one increases, the other one decreases. So in this way, looking at the R value, we can know whether there is a relationship that exists and what is the kind of relationship and also the strength of the relationship.
Okay, that is true. I just want to understand in this way, suppose we want to get the opinion of Delhi University students about the liking of the television programs.
Okay.
So the number of variables may be 2, 3, 4 on which we can judge.
Yes.
And through this example, can you explain where correlation and regression will help us to understand that?
So the first thing is that we have to find out the attitude of Delhi University students, and the first thing is that the variables have to be metric. So attitude has to be measured on a say 0 to 9 point scale, etc. Okay. Then this attitude may depend on various things. The age of the respondents. Okay, it may depend on for how long have they been staying in Delhi. It may also depend on their income and other demographic and psychographic variables. So all these variables become independent variable. Once we calculate this data, we can use regression to know that whether the Delhi University students have a positive attitude toward Delhi University or not, and whether this attitude depends on either income or whatever variables we have taken in the model. It may also indicate which of these variables is more explaining the attitude towards the Delhi University.
Okay. So one is attitude, and then the other was the television program.
Attitude towards the television program.
Yes.
That can also be calculated on a, or which can also be asked on a 0 to 7 or 0 to 9 point scale.
Okay. So I think students must have enjoyed the lecture, and they now come to know how to calculate the correlation and regression, and also what is the practical aspect, and where we can apply in a more appropriate way. So I think this is enough, and tomorrow we'll have one more lecture on this in the series of our statistical tools used in the research methods. Yeah. So friends, we'd like to conclude the lecture here, and I thank all of you for watching the lecture, and on your behalf I thank Dr. S.K. Pandey for giving such a wonderful lecture. Thank you very much.